Hey everyone, and welcome back to the channel. Today, we're diving deep into something that's all around us, pressing down on us every single second, yet we almost never notice it. I'm talking about atmospheric pressure. It sounds like a heavy topic, right? Well, it literally is. But I promise, by the end of this video, you'll see it in a whole new, fascinating light. So, what exactly is atmospheric pressure? Imagine the air above you. It's not just empty space. It's a massive ocean of gas molecules: nitrogen, oxygen, argon, and a bunch of others. All these molecules have weight. Atmospheric pressure is simply the weight of that entire column of air, from the top of the atmosphere all the way down to the ground, pressing on a certain area. Think of it like this. If you're at the bottom of a swimming pool, you can feel the weight of all the water above you. The deeper you go, the more pressure you feel. Our atmosphere works the same way. We're living at the bottom of an ocean of air. At sea level, the pressure is about 14.7 pounds per square inch. That means on every single square inch of your body, there's a weight equivalent to a bowling ball pressing down. Now you're probably thinking, wait a minute, if there's that much pressure, why don't I get crushed into a pancake? That's a great question. And the answer is equally cool. Our bodies are not hollow. They are filled with fluids and gases that push outward with the same force that the atmosphere pushes inward. This creates a perfect balance, an equilibrium. It's why you don't feel the pressure. Just like a fish deep in the ocean doesn't feel the immense water pressure around it. Our bodies have evolved to live in this high-pressure environment, but this pressure isn't constant, it changes. The most significant factor that affects atmospheric pressure is altitude. As you go higher up, say, climbing a mountain, there's less air above you. The column of air gets shorter, so its weight decreases. Consequently, the atmospheric pressure drops. This is why mountaineers often need to acclimatize or use supplemental oxygen. At the top of Mount Everest, the air pressure is only about 1/3 of what it is at sea level. The air is thinner, meaning there are fewer oxygen molecules in each breath you take. This change in pressure can have some weird and wonderful effects. Have you ever noticed that a bag of chips you bought at sea level looks like it's about to pop when you take it up a mountain? That's because the air trapped inside the bag is at a higher pressure than the air outside, so it pushes the bag outwards. It's also why water boils at a lower temperature at high altitudes. Boiling happens when a liquid's vapor pressure equals the surrounding atmospheric pressure. With less atmospheric pressure pushing down on the water surface, the water molecules need less energy, or heat, to escape as steam. So in Denver, the mile-high city, water boils at around 95 degrees Celsius, not 100. This means you have to adjust your cooking times for things like pasta and eggs. So how do we measure this invisible force? We use an instrument called a barometer. The classic mercury barometer, invented by Evangelista Torricelli in the 17th century, is a simple but brilliant device. It consists of a glass tube, closed at one end, standing upside down in a pool of mercury. The weight of the air pushes down on the mercury in the pool, which in turn supports a column of mercury inside the tube. When the atmospheric pressure increases, it pushes the mercury column higher. When it decreases, the column falls. The height of this mercury column is a direct measurement of the air pressure. That's where terms like inches of mercury or millimeters of mercury come from in weather reports. Of course, we don't really use big tubes of toxic mercury anymore. Modern barometers are typically aneroid, which means without fluid. An aneroid barometer uses a small, flexible, sealed metal box called an aneroid cell. This cell has had some of the air pumped out of it. When the atmospheric pressure changes, the box either expands or gets squeezed. This tiny movement is then amplified by a system of levers and springs, which moves a needle on a dial to show you the current pressure. Your smartphone and many smartwatches have a tiny, solid-state barometer built right in, using a micro-electromechanical system, or MEMS, to detect pressure changes. It's amazing technology. Now, Why should we care about measuring atmospheric pressure? Well, it's one of the most critical variables in weather forecasting. Changes in pressure tell us about the movement of air, which is essentially what weather is. Generally speaking, high pressure is associated with stable, clear, and calm weather. In a high-pressure system, the air is sinking. As it sinks, it warms up and dries out, which prevents clouds from forming. Think of beautiful, sunny days with blue skies. That's typically high pressure at work. On the other hand, low pressure usually means unsettled weather. In a low-pressure system, the air is rising. As it rises, it cools and the moisture within it condenses to form clouds and often precipitation like rain or snow. Storms, hurricanes, and tornadoes are all extreme examples of very low-pressure systems. So, when a meteorologist says a low-pressure system is moving in, it's your cue to grab an umbrella. A rapid drop in barometric pressure is a classic sign that a storm is approaching. By tracking these areas of high and low pressure, which we call highs and lows on weather maps, forecasters can predict how air masses will move and what kind of weather they will bring. Let's do a little home experiment to visualize this. You don't need a fancy barometer. All you need is a glass jar, a balloon, a rubber band, a straw, and some tape. Cut the balloon and stretch the flat part tightly over the mouth of the jar, like a drum skin. Secure it with the rubber band. This creates a sealed chamber of air inside the jar. Now, tape the straw horizontally onto the center of the balloon skin so it acts as a pointer. When the atmospheric pressure outside the jar is high, it will push down on the balloon diaphragm, causing the end of the straw to point up. When the atmospheric pressure outside is low, the higher pressure air trapped inside the jar will push the balloon diaphragm up, causing the straw to point down. You've just built a simple aneroid barometer. If you place a piece of paper behind the straw and mark its position every day, you can track the changes in pressure and see how they correlate with your local weather. Beyond weather, atmospheric pressure plays a role in so many other things. It's what allows us to drink through a straw. When you suck on a straw, you're lowering the pressure inside it. The higher atmospheric pressure outside then pushes the liquid up the straw and into your mouth. It's not you pulling the liquid up, it's the atmosphere pushing it up for you. Airplanes rely on principles related to air pressure to fly. The shape of an airplane's wing, called an airfoil, is designed so that air moves faster over the top surface than the bottom. According to Bernoulli's principle, faster moving air has lower pressure. This pressure difference creates an upward force called lift, which overcomes the plane's weight and allows it to fly. Even our own breathing is a function of pressure changes. When you inhale, your diaphragm muscle contracts and moves down, increasing the volume of your chest cavity. This lowers the pressure inside your lungs compared to the outside atmosphere, and air rushes in to equalize the pressure. When you exhale, your diaphragm relaxes, the volume of your chest decreases, the pressure inside your lungs becomes higher than the outside, and air is pushed out. So, from predicting tomorrow's weather to helping us fly across continents and even take a simple breath, this invisible force of atmospheric pressure is fundamental to our world. It's a constant presence, a powerful force shaping our environment and our lives in countless ways we rarely stop to consider. The next time you check the weather, see a plane in the sky, or even just take a sip from a drink, I hope you'll remember the amazing physics of atmospheric pressure at work. It's a perfect example of how science can reveal the extraordinary hidden in the ordinary. Thanks so much for joining me today to explore this fascinating topic. If you enjoyed this video and learned something new, please give it a thumbs up and consider subscribing for more deep dives into the world around us. Let me know in the comments if you've ever experienced any strange effects of pressure changes. See you in the next one.